One of the most easily understood physical properties is perhaps the shape of an object. And if we take a simple camera, it has this kind of standard shape. Now, let's move down a level. Let's go to the level of atoms, to the level of subatomic particles. Among subatomic particles, there is a standard but very interesting particle called the electron. An electron should also have a shape. After all, if we're talking about the existence of this particle, then most likely it should also have some kind of standard shape. But the paradox is that in fact the electron doesn't really have a standard shape. So how is it possible that the electron seems to have some material properties but no shape at all? That's the question we have to answer today. All of this is interesting because the circumstances we'll discuss today, specifically regarding the electron, also apply in many ways to other quantum particles, of which there are a great many. Nevertheless, for now, let's focus on the electron. Well, if you don't watch my channel, if you skip my videos, then you probably don't know yet that particles like the electron don't have a shape in the literal sense of the word. You can touch this camera, you can measure it with a ruler, you can place it next to other cameras like it, and it will occupy a certain volume. And all of this essentially is described by the shape of this camera. It's quite obvious that if the camera has a protrusion like this with a lens, then stacking one on top of another will be harder than if the camera were flat on all sides. All of this is determined by what we're discussing in terms of shapes. Furthermore, any particle that is considered a material particle, apparently, must also be required to possess a specific geometric shape. And of course, we always really want to use the analogy that an electron is like some kind of little ball, a baseball or something like that, and that this ball can somehow be used. Again, let's look at standard educational materials. Let's look at the typical analogy. And very often we see that the electron is indeed compared to a little ball. Moreover, not only electrons, but also photons, and in fact many quantum particles are compared to a ball. Again, if you regularly watch my channel, you already know that this is completely incorrect, and that quantum particles and particles at the level of the electron only have material properties within certain limits. In fact, if we speak in such abstract terms, the electron, it's something unclear, possessing only just some material properties. That's why all the comparisons based on the idea that we have some kind of little balls flying around, balls bumping into each other, balls trying to squeeze through a crystal structure made up of atoms, where we imagine the electron gas this way, all these models are actually not very accurate. Moreover, I'll tell you something interesting now. How do you imagine it? The process of electric current passing through a metal sample. Again, guided by those models that you constantly encounter, you most likely imagine the crystal lattice of a metal. The crystal lattice of a metal most likely consists of lattice points where atoms are located, and between these lattice points, electrons dot around. But even at this level, this model is completely incorrect. And it's incorrect because in fact the electrons aren't darting around anywhere. It is much more accurate, according to modern understanding, to say that electrons are fixed near specific atoms, belong to a particular atom, and when energy is applied, illustrating electric current through a conductor, these electrons begin to move, forming something like a wave, and this wave, like a Newton's cradle, propagates throughout the entire structure. However, you can find plenty of 3D models where the electron is depicted as a little ball, which is fundamentally incorrect, and it is also incorrectly shown moving through the crystal lattice, getting caught on the nodes of this lattice, and pushing other electrons, whereas in reality the process looks a bit different. The process actually looks like this. Essentially, electrons move within the conductor. Very, very rarely. Yes, indeed, there are individual electrons that travel through the conductor, and these individual electrons behave quite differently from how, in fact, we might imagine them to. So keep that in mind. But besides that, keep in mind that, in fact, the very illustration of an electron as a little ball is fundamentally incorrect. So what then is correct? Let's ask the scientists about this. Well, there are actually two interesting theories here, not just hypotheses, but actual theories. I'm afraid of making a mistake because people constantly point out that I confuse theories with hypotheses. Well, alright, I hope you'll forgive me because I hope I'm conveying the main idea correctly. And in this case, electrons are described by classical physics in two ways. One of the approaches used in standard physics is to describe the electron as a point particle. The other method used in physics already relies on certain quantum properties of the electron. The electron is described as a wave function. The electron becomes a probability density. And here we encounter an absolute paradox. It turns out that we are trying to imagine a point that is smeared across the entire universe. Now just try to process that yourself. Frankly speaking, what absolute nonsense this is. How can we have a point-like particle? How can we have a point-like object? How can it, first of all, occupy a huge space? And secondly, how can this point-like object spread its properties over a certain region, even if not infinitely? And this is where things get really interesting. From this point on, you need to listen very carefully and pay close attention to everything I'm going to tell you. Let's start by clarifying what a point-like particle actually is, what physicists mean by a point-like particle. To some extent, it's a kind of mathematical abstraction. And this mathematical abstraction forms the basis of the entire standard model. What does that mean? Well, let's recall what a point is in geometry. Most likely you imagine that you put a dot on a piece of paper with a pen, this very dot. But no, my friends, in the general sense, this school-level understanding of a point is completely incorrect. And this school-level understanding of a point comes from the fact that, at that stage, no one really thinks about it. Your teacher calls you up to the board, draws 2 points, point A and point B, and says, draw a straight line through these 2 points. And it's around this stage that you get the idea that a point it's some kind of object that's drawn with chalk on the board. But in fact, from the standpoint of strict mathematics, it's impossible to draw a point on the board. What you drew on the board is already at least a 2-dimensional object. It's already an object that has 2 dimensions. And this object can be measured in 2 directions. Moreover, if you dig deeper, it turns out that this object can even be measured in 3 dimensions. That is, in principle, you can also measure the thickness of what remains on the board. But that's getting a bit too pedantic. Usually, at this point, people say you've completely lost your mind. Nevertheless, I believe such a precise approach is crucial for the scientific understanding of reality. But that's not the main point of our conversation now. And so, when we draw such a point on the board, we always imagine that a point is this kind of object. In reality, strict mathematics tells us that a point is a 0-dimensional object. But what is a 0-dimensional object? It means that it only has coordinates. It means that you can't actually place this coordinate like a point on paper. This means you can't place this coordinate on the board, so it will simply stay as it is. Just like that, click, and that's it. It's simply coordinates. I repeat this so much, I try to explain it so vividly so that you understand this special aspect. Why does this surprise us in this context? Because if we're talking about specific particles, if we're saying that we're working with electrons, if we say that this particle is in a way material or at least has some material properties, then we can no longer approximate this point, which is essentially nothing, which is a 0-dimensional object, and essentially indicates where the particles are, yet it has no dimensions, no measurements, and in no way can be mentally associated with what a particle could actually be. Nevertheless, all of standard physics, the entire standard model of physics, is based precisely on the idea that all standard-type particles are represented in just this way. And for a physicist, an electron is a 0-dimensional particle. It is a 0-dimensional particle that has 0 dimensions. Essentially, all we know about the electron is the point where it is located. At the same time, various ideas are imposed on this point, suggesting that this point has certain properties. In order to move away from these purely mechanical concepts, where the electron is just a point, the idea of quantum physics was introduced into physics. It is clear that the emergence of quantum physics is not related solely to the electron itself, and that quantum physics is not aimed at explaining only the properties of the electron. Nevertheless, it is precisely quantum physics that, in this context, adds to the electron. Those very properties that, in fact, make an electron an electron. The quantum physics view of this particle becomes quite strange. And in this context, we move from the idea of the electron as a simple point to the electron becoming a certain region. There is a lot to discuss here. One could talk about the specific quantum properties of the electron, discuss the properties of the electron as a quantum particle, but what interests us right now is specifically the shape of the electron. What can we say about this? And what experiments or real-life tests exist that confirm our entire approach is correct? But first, let me say again that in principle, for physics, the electron is a certain particle that is simultaneously point-like and at the same time spread out across the entire universe. These interesting properties, of course, are not just made up out of thin air. They follow from a number of experiments, from a series of theories. They are confirmed mathematically, and they manifest themselves in practice. So how did physicists find out, for example, that the electron is a point-like particle? Was everything really built solely on this crazy abstraction that there is a 0-dimensional object that is just a point? No, in fact, there are, roughly speaking, a set of methods that allow us to determine this, and one of these methods is particle scattering in a collider. How can we even tell if a particle is made up of something? How does the experiment work that allows us to understand that this particle is a lepton, that is, that it is not made up of anything, like the electron? Or does this particle decay into other quarks, like many other subatomic particles? Particles in particle accelerators are of different types. As a rule, these are colliders, the very same colliders similar to the Large Hadron Collider. Sometimes the LHC itself is used to accelerate these particles to enormous speeds. Next, there are certain special targets into which these particles crash. At the moment when a particle collides with another particle, an interesting process occurs. The interesting process is that the enormous energy causes the particle to break apart into its constituent parts. Right now, I am greatly exaggerating this process. I am really simplifying what is happening. Perhaps I am even making a few mistakes, but nevertheless, the logic in any experiment is always the same. You need to collide two objects hard enough so that one of the objects, or maybe even both, break apart into their components. Roughly speaking, it's like crashing a car into a wall and seeing which screws fall out. And this method has proven itself to be very effective. This method has proven to be so effective that many theoretical predictions once made by mathematics have become reality in practice. Thanks to precise detection, we have been able to observe many constituent parts of various subatomic particles, and to understand that they really are made up of something. But that didn't work out with the electron. However, in one of the videos on the channel, I'll leave a link in the suggestions or description, I explained that the story of the electron structure is much more complicated than physicists would like it to be. In the standard understanding, physicists reduce everything to the idea that the electron consists only of itself. It is simply an electron. But it is by no means impossible that, in reality, the electron has a complex internal structure. I won't repeat the entire essence of that video on the channel about this topic right now. I just recommend you watch that video. And now, we'll say that essentially at this moment, in this context, we've stopped at the point that the electron does not fall apart. And based on this, we've concluded that this particle is most likely point-like. In reality, this logic doesn't seem reasonable. Why? Because we collide the particle, see that it doesn't fall apart, and say that it's point-like. But at the very least, this allows us to confirm that the mathematics used in the standard model is correct. That is, the calculation mechanism for a point-like object is confirmed in practice by what we observe about how this object behaves in real experiments. But nevertheless, you have to admit, it's very strange that an object which could very well have some dimensions becomes a point-like object, and this conclusion is drawn simply because it didn't break up into anything. In many ways, the conclusion we have just reached is supported by other physicists, and they agree with the statement that the electron can be a particle of infinitely small size, or better to say, a particle of very small size. But at the same time, this does not mean that it is zero-dimensional, and it does not mean that it is, after all, just a point. The fact that nothing could be shaken out of the electron when it was collided with something else by no means implies that the electron is a tiny, point-like zero-dimensional particle. And this whole story of the standard model, which assumes that the electron is a zero-dimensional particle, that the electron is simply a point, is actually needed only to statistically describe the behavior of electrons. In other words, this means that, in a physical sense, the electron is most likely not a point, and this whole story about it being a particle, a point, is an excessive simplification of the problems. And here, our knowledge that the electron apparently has some size comes to our aid. If you open a textbook and look up the size of the electron, you will see the standard value. I'll show it on the screen now. This is the distance at which the electrostatic self-repulsion energy would be equal to the energy of rest mx squared. So essentially, this is not a real value. Essentially, this is again a calculated value. And in fact, once again, we end up with a kind of mathematical anecdote, some mathematical mumbo-jumbo. Nevertheless, it is quite commonly used. But again, look, based on the fact that we did not consider the electron as a zero-dimensional object, but as an object with size, and said that according to calculations, this is the value we get. This is also something worth thinking about, but there is not a word here about the surface of the electron, or about what shape the electron should have. We don't see that. So it turns out that knowing the electron is supposedly a point particle, and knowing that it is kind of point-like but still has some size, hasn't really helped us figure out what shape the electron should have. Let's turn strictly to the quantum world and see what shape the electron should have there. We have already said that, according to this view, the electron is a certain probability density. This probability density is described by the standard wave function, and this wave function tells us which properties of the electron we can actually find, calculate, and measure, and what properties the electron should have as a result. Essentially, we have exactly that situation, that very system, in which nothing exists until the moment of measurement. Nevertheless, here the paradox reveals itself in an even more striking way. It turns out that a point-like system, which we seem to be able to precisely determine, a point-like system that we can locate at a specific point, and which the standard model seems to be able to do, at some moment ends up being smeared out over a certain volume. But quantum physics counters this question by saying that, well, the system is point-like, but there is a certain region of probability. Alright, you will find this point, but only with a certain probability. And this is where the collapse with measurements comes to the rescue. Those very moments that are characteristic of the entire quantum world. The very moments that make Niels Bohr go crazy. And the very moments that make this world completely illogical for any ordinary person to comprehend. Nevertheless, whatever is happening there, we come to one conclusion. At the moment of measurement, the quantum function somehow either collapses or something happens to it, and in some way the most probable state manifests itself. And so we get that very point we talked about, the very point that already possesses strange properties, the very point that is supposedly smeared out. And the specific explanation for why this happens is in fact not so important here. It could be the many worlds interpretation, where we have a huge number of universes, and in one of those universes, it just so happened that the point is right there, with those particular parameters and properties. It could be the logic of the pilot wave, where this pilot wave already contains specific properties. Or it could be determinism based on hidden variables, which many people strongly criticize. So, one way or another, quantum physics, quantum perception of the world, again, does not give us a direct answer as to what form the electron takes. And again, we are faced with the core of the problem, where we have a certain material object that we want to touch, a material object that makes itself quite apparent when it shocks your fingers from an outlet, and a material object that possesses a number of physical properties. And so, it apparently must have some kind of form. From the quantum world, it follows that the shape of the electron is some kind of vague, diffuse cloud, where it can be a point in a specific place with a certain probability. Well, does that really mean anything? For the material world, that doesn't mean much, and once again, the shape of the electron becomes unclear. We could take the simple route and say that the electron simply has no shape at all. But nevertheless, we also acknowledge that electrons interact with each other and with other objects. And if that's the case, then at some level, somewhere, it must happen, right? The thing is, one form must encounter another. After all, we need to localize these systems in order to talk about interaction, don't we? Here, physics takes a very clever and interesting approach. It says that, in a way, the system with the point-like model of the electron is correct, that the standard model works, and that all the mathematical calculations help us. And at the same time, it says that quantum physics is also correct, and that the calculations from quantum physics also work. Well, fine, let it be so. Let's imagine that an electron is some strange region of space with an unclear shape, maybe like jelly, maybe something else entirely. It doesn't have any material analogy, but we still need to somehow measure it. And here, specific experiments pick up on this idea and use certain properties of the electron in order to say that it has some definite shape. So what can we actually observe there? What can we touch in order to talk about its shape? Well, it should be said right away that of course we can't actually see or touch anything. Seeing it is completely out of the question, as they say, because we simply cannot see particles at that scale. I've talked about this many times on the channel, and we often discuss the fact that there is such a concept as diffraction limits, there is also the concept of scattering limits, and there are many properties that essentially prevent us from seeing the electrode. Moreover, even when we talk about detecting certain nodes of a crystal lattice, we can say about the distribution of certain waves and other effects associated with this. But with the electron, so to speak, we practically never can. So what can we actually do to somehow feel this electron? And even more so, what can we do to somehow see its shape? Well, it's probably logical to assume that we need to use some kind of indirect measurement methods. But indirect measurement methods are essentially like dumping a bag of flour on an invisible ghost. Indirect measurement is much more interesting. There are a variety of different methods here, but almost all the methods we mention, almost all the methods we discuss, rely on the fact that under very specific experimental conditions, the electron should deviate from some standardized and expected characteristic property. One of the most common methods is the electric dipole moment method, EDM. Essentially, this technique involves placing the electron in a strong electric field and observing how the electron behaves, how it responds to it. From different sides, this electron, roughly speaking, is blown on by the electric field. Again, I'm using very simple and rather primitive analogies which may not even be entirely accurate, but I sincerely hope that I'm conveying the essence of the experiment correctly. So what happens is this. This electron is placed in an electric field. This electric field, in a sense, washes over the electron and causes the electron to interact with the electric field. And if the electron has an irregular shape, then the effect, how much the electron starts to spin, rotate, or move, will be determined by which side the electric field is washing over the electron from. If the interaction is the same from all sides, this will mean that the electron does not have any particular deviation from its ideal state. It's not hard to guess here that if we're talking about an ideal state, then it must be something perfect. And what is the most perfect thing we have in physics? What shape does a drop of water take when it's in zero gravity? It's easy to recall those very videos you've seen about space, easy to remember the videos shown from the International Space Station, and to recall how water takes on the shape of a sphere. Why a sphere? Yes, because it's the ideal perfectly balanced shape. And so in this case, we proceed from the idea that if nothing is spinning the electron when it is placed in different types of electric fields, then most likely it has a perfect shape. The perfect shape is a sphere, as we've already established. And that's why we assume that the electron has the shape of a sphere. And it would seem that this is the answer to the question. It would seem that we've already said that the electron's shape is a sphere. We've determined experimentally that the electron behaves like a sphere. We reduce this experiment to such a simplification that this sphere does not spin under certain conditions, and having no particular orientation in space, reacts the same way in all directions, which means it is perfect. And it would seem that we've answered the main question of this video, but it's still too early to say that. We need to take the concepts we have in physics regarding the point-like nature of the electron, regarding the fact that it's a certain probability density, and apply them to the idea that it's a sphere. In principle, that's exactly what scientists do. They take the idea that the electron is a point-like particle. They say that this point-like particle has a certain probability of being detected, and that all of this is still concentrated in a spherical manner. So what we end up with is a kind of unicorn, or a tenetolka, or katapes, call it whatever you like. But one way or another, we arrive at the idea that this is a sphere with fuzzy edges, a sphere described by probabilistic models, a sphere in which, essentially, the probability of the electron being located there is hidden. The paradox, which is based on the fact that a point-like particle turns out to be smeared across the entire object, is largely resolved by the fact that we say these are different questions. When we ask what an electron is and what its shape is, we have to say that it is a point-like particle, as follows from the Standard Model, and is governed by the laws present in standard physics. When we talk about how an electron behaves, we have to use the concepts of the quantum world and apply them to the fact that it is a point-like particle. And essentially, we answer the questions of how and where differently. That is, the question of where is in any case a deterministic moment that manifests itself during measurement and is a point, while the question of how concerns the behavior of the electron, which is related to the fact that it has a certain probability region. The electron is indeed point-like as an object, but at the same time it behaves as a quantum system. And how do quantum systems behave? We have already discussed this many times. And essentially, probably when we talk about how to even imagine an electron with a specific shape, this is a question similar to asking how to imagine, well, for example, the probability that when you toss a coin, the chance of getting heads or tails is 50-50. It's a question of about the same level. Here, apparently, we have to accept that particles of this kind simply do not behave the way material particles are supposed to behave. Essentially, in my opinion, the whole problem stems from the fact that physicists do not fully understand what they are dealing with. And no, this is not just a flashy, loud statement, it's actually a real assertion. Look, for example, when we take something on the scale of our material world, take this wonderful camera, well, to some extent it's not that wonderful, but that's beside the point. This not so wonderful or very wonderful camera exhibits certain properties. I mentioned these properties at the very beginning of the video, and basically it's easy to visualize them mentally. For our practical purposes, these properties are sufficient. In order to apply certain physical laws to work with an object like this camera with this shape, we have enough knowledge, and this level in principle is exhaustive. Obviously, if we dig down to the structural level of this camera, we'll see many interesting processes there, up to and including quantum tunneling, which also isn't fully explained. But one way or another, when we move to the quantum level, we encounter objects. With objects, not particles, not material bodies, but specifically objects that behave in such a strange way that they are simply described by mathematics. And this is where things get really interesting. We have a certain mathematical world that exhibits some properties of the material world. For science, there's nothing frightening about this, but for the level of popular science, for the level of understanding that we have, for the level at which we are trying to make sense of things, it's a real catastrophe. By and large, we just have to accept that reality is much deeper, reality is much more interesting, and reality is far more complex than we can even imagine. And physics often encounters this, while scientists, if you pay attention, treat it quite normally. So the fundamental core objective of this entire video, and the primary challenge and significant hurdle in understanding everything we've discussed, is precisely that we need to transfer a complex system with an ambiguous and elusive nature to the level of our tangible material perception and understanding. And in this context, the concept of the electron's shape becomes completely insignificant. The shape of the electron becomes an additional property that, in principle, does not apply to the electron at all. Nevertheless, if you want a simple answer to this question, we can always refer to all the reasoning we've discussed above. Essentially, to answer this very briefly, the electron has a spherical shape, but not a sphere with a clear boundary, rather one with a blurred edge. This sphere to some extent illustrates the probability of a particular event occurring when measuring this electron. And essentially the sphere is a way of representing the probability distribution. This sphere does not rotate in any way, nor does it spin in any fields, and this confirms that it is indeed a sphere. And the fact that the electron is a point particle follows from the fact that inside this sphere, when measuring a specific property, we essentially arrive at that very point which exists in the standard model. So very briefly, what is an electron? Well, essentially it is a blurred sphere. I think for a popular science level, such a definition is more than sufficient. And of course, I hope you found this interesting and that the video was useful. If you found the answer to your question, if you thought the material was valuable, then as always, I kindly ask for your support. Support the project with likes, and as always, I ask you to visit Boosty, follow the link and subscribe to Boosty. And of course, I want to say thank you to everyone who is already supporting the channel on Boosty. And as always, I want to thank everyone who watched the video up to this point. Once again, I ask you to like this video so it gets promoted on YouTube. Well then, until next time, all the very best to you. Goodbye. Very soon, we'll talk about new and interesting physical aspects of the world around us.